Hello class, on this video we're going to continue talking about systems of linear equations. Now that we've seen how to rewrite the systems using matrices, we've seen the properties of how to multiply matrix times a vector, how to add matrices of the same dimension, and then how to take determinants of 2x2 matrices. And finally, we saw how to verify whether a vector is a solution to a system. Now, what we're going to see is that basically all of the theorems we saw in the previous chapters, or in chapter 4, also extend to systems of linear equations. Why? Because what matters is that the equations are linear. Linearity is what matters. Right? So everything we saw in chapter 4 extends basically word by word to this chapter 7, talking about systems of linear equations. Okay? So, for the existence and uniqueness of a solution for an initial value problem, right? Let the entries in the matrix A and the vector G be continuous on a common interval I that contains T naught in its interior. Then there exists, so it should be a there instead of a the. Then there exists a unique solution to the system x prime equals ax plus g, subject to the condition x of T naught equals x naught on I. Now notice that this assumes that your derivatives, if there was something multiplying the derivatives on each equation, you divide it by that, right? So this is assuming that whatever is multiplying the derivatives is just the coefficient 1. Okay. Right. So as long as that's the case, you only have to check the continuity of each entry in A and each entry in G. As long as that's the case, then, and as long as on whatever interval, and as long as that interval contains the input T naught, then this initial value problem has a solution. And now, when it says something like x of T naught, just means, okay, x is, each entry is a function, just like we saw in the previous example. Our x2, for example, was this. So what's x of T naught? Just replace the t's with T naught. So if T naught is 5, replace the t's with 5s, right? That's all that means. Right? So the exact same theorem as before, just the things that you have to check change a little bit. Another theorem that extends very easily is the superposition principle. So let x1, x2, up to x of k be solutions to the homogeneous system. Right? This is the system where there's no vector g. Right? So there's no g sub i's at the end of the dependent of each ODE, right? Or the g sub i's are all 0. Okay. So suppose you have k solutions, which now are vectors, to the homogeneous system. And again, that means that g of t is 0, right? The 0 vector, each g sub I is 0, right? On some common interval I. So all of these vectors have to be solution on a common interval I. Then, as we saw in chapter 4, any linear combination of these vectors is also a solution on I. So again, everything generalizes to the system case very easily because we're working with linear equations. And linearity is the key. So let's see an example. So verify that C1 e to the times x1 as in the previous example and C2 times x2 in the previous example is a solution to the same ODE for any C1 and C2. Right, so let's do the work again. Right, so since we already defined everything, I'm going to be a little bit faster. But our A was given by 1, 3, 5, 3. And again, let me change the x1 and x2s to x and y's because we're only using 2 variables. X, y, x, y. Okay, that's our matrix. So we're looking at the system. X prime equals ax. So let's verify. So first, what we're going to do is, so there's a couple ways you can do this. The way I'm going to do this is like this. So first, I'm going to combine these into one single matrix. Oh, which reminds me, there's actually something I forgot to verify. So how to multiply a constant times a matrix. So let me add this here. Yeah, so one more operation, which is pretty straightforward. If we have a constant, let's say, let's call it d, times a matrix, and so a matrix A11, A12, A21, A22. This is just the matrix where you multiply each entry by D. So D, A11, D, A12, D, oops. Yeah, so sorry, I forgot to write this. A21, D, A22, right? And the same for a vector, where D is a constant. Doesn't have to be, for most of our purposes, it is going to be a constant. But so let's say where D is a function, just more generally a function. Doesn't have to be a constant. Similarly for a vector. So suppose we have a vector that looks like this. Just multiply each entry in the vector by D. And okay, for sure, this is the last thing I needed to show you, so I'm sorry. So let's go back to the example. So again, there's a couple ways you can verify this. The easiest way is write X as a single matrix. So right now we're adding two vectors. I want to write it as a single vector. So let's simplify this. So X is given by C1, this thing, plus C2, 3 e to the 60, 5 e to the 60. Right, so let's try to write this as a single vector so we can plug it into the equation. So first, let's multiply each of the constants inside. We have the constant C1 multiplying the first vector, so we can just move that in. So multiply each entry by the C1. Same for the second part, there's just C2 multiplying this vector. Let's multiply each entry in the vector by C2. Now, how do you add matrices of the same dimension? You can verify. Both here have 2 rows and 1 column, so the dimensions match. Right? So just multiply entry-wise. So this becomes C1 e to the negative 2t plus 3C2 e to the 60. We're just adding term by entry. This one becomes negative C1 e to the negative 2t plus 5C2 e to the 60. And this is the vector that we're going to plug into our ODE, or into our matrix equation. Okay? So we need to find, this is our x, we need to find x prime. And so let's find x prime. So x prime, just take the derivative of each entry. So derivative of the first entry by the chain rule is negative 2 C1 e to the negative 2t plus 18 C2 e to the 60. So I think I did that chain rule right. Okay. Derivative of the second entry is, so bring the negative 2 down by the chain rule. Oops, sorry. So we get, so we get negative 2 times negative C1. So negatives cancel. So I get 2C1 e to the negative 2t plus 30, right? 6 times 5 is 30. C2 e to the 60. Now, let's plug everything into the ODE, or into the matrix equation, and verify that everything works. So AX should be equal to this. So let's simplify AX. A is given by 1, 3, 5, 3. X is this vector here. I think I can just, let me just write it again. I was going to copy paste it, but it's okay. Okay. Now again, this is a matrix times a vector, so you can just do it row by row. So let's start with the first row. Okay. So multiply the first entry in the first row times the first entry in the vector. That's going to be 1 times this whole thing. So 1 times this whole thing. It actually might not fit, so let me just work downwards instead. So they have more space, right? So 1 times this whole thing. Okay. And then plus the second entry in row 1 times the second entry in the vector. And you know what? Let's change colors. I think too much red is actually not good. So let's change to orange, for example. So again, the first part, a little bit bigger. So 1 times the first entry in the first row times the first entry in the vector. Plus second entry in the first row times the second entry in the vector. That's just going to be 3 times negative C1 e to the negative 2t plus 5c2 e to the 6t. Okay. Now go to the second row. First entry in the second row is 5 times the first entry in the vector. That's C1 e to the negative 2t plus 3c2 e to the 6t plus second entry in the second row times the second entry in the vector. That's 3 times negative C1 e to the negative 2t plus 5c2 e to the 6t. And then we simplify this whole thing. So let's just combine like terms. We have 1c1 e to the negative 2 minus 3c1 e to the negative 2. So 1 minus 3, that's minus 2. So minus 2c1 e to the negative 2t. I'm just doing the first row first, and I have 3c2 e to the 6t plus 15c2 e to the 6t. So that's 15 plus 3, that's 18 of them. So plus 18c2 e to the 6t. Now let's simplify the second row. I have 5c1 e to the negative 2t minus 3c1 e to the negative 2t. So 5 minus 3 is 2 of them. And then simplify the other one. We have the other exponent. So I have 5 times 3c2. So that's 15c2 e to the 6t plus 15c2 e to the 6t. So I have 30 of them. Okay. And this should be equal to the derivative, and they match. So this is, in fact, a solution for any constant C1 and C2. Oops. Yeah, so this matches this, the derivative. So we just verified that for any C1 and C2, these are solutions. Again, we already knew this is the case because of the superposition principle, and because we already knew that both of these were solutions, but we verified that it works. Just as more practice. Now, linear dependence and independence also generalizes the same way. So let x1, x2 up to x sub k be solution vectors of a homogeneous system, again, where you don't have a vector g to add on some interval I. Then we say that the x of I are linearly dependent on I if there exists C1, C2 up to Ck constants, right, not all zero. So in this case, they are constants, just like in chapter 4. And I say in this case because when I gave you the multiplication, this d here, when you multiply a matrix times something, doesn't have to be a constant, right? So it can just be a general function. But here, when I have C1 times X1, the C sub i's are all constants. So it's the same definition as in the chapter 4, right? You need constants, C sub 1, C sub 2, up to C sub k, not all zero, such that this equation has solutions for all t on I, on some interval I. If there are no constants, not all zero, right, for which there is a solution for this on some interval I, then the functions are said to be linearly independent. So this is the same complicated definition that we used in chapter 4 and in chapter 3. However, we also have the Wronskian, right? So I'm not actually going to go over any examples of using this definition as it is. We're just going to go ahead and use the Wronskian. So theorem 2. So suppose our vectors are given by these entries. I suppose x1 is x11, x21 up to xn1. X2 is x12, x22 up to x2m, right, etc. Now notice here, again, I follow the same thing. And I follow the subscript pattern, right? So the first subscript is always telling you what row you're in. However, in this case, the second subscript is telling you what solution vector you're a member of. So for example, all second subscripts in the vector x1 are 1 because these are entries in the first vector. All second subscripts in the second vector are 2's, saying that they are... Oh, yeah, so I did a typo there. Yeah, I did a typo here. This just should be... And 2... Yeah, there. Yeah, so all second subscripts in the second vector are 2's, right, because they're in the second vector, and all... I did it backwards again. Yeah, sorry about that. So it should be... Oops. Yeah, so this should be x1n, x2n, all the way up to xmn. So now all second subscripts in the nth vector are n's because they're in the nth vector. And again, the first subscripts all tell you what row you're in. Okay. So suppose we have n vectors, right? And again, they don't have to be solutions for a system of ODEs. You can do this more generally, but in our context, they are solutions for ODEs, right? Right, so suppose you have these n vectors, which are solutions for the homogeneous ODE on I. Then the set of solutions, or these x of 1, x2, up to x of n, are linearly independent on I if and only if this Wronskian is not equal to 0. Now, the Wronskian here is defined a little bit different. Basically, each row is just the vector x, right? So you don't have to compute any derivatives or anything like that. Just, okay, x1 is row 1, x2 is row 2, xn is, column, sorry. x1 is column 1, x2 is column 2, xn is column n. Okay, so again, the vectors are the columns of your matrix, right? And it's the same condition. On whatever interval this is not equal to 0 for all t, then your solutions are linearly independent there. Right? So again, you don't have to take any derivatives, just plug in each vector as a column in this matrix. So as simple as that. Okay. Let's see an example. Determine on what interval, if any, are x1 and x2 linearly independent. Now notice that these are the same vectors as in our previous example, so example 3 and example 2, right, which we already found were solutions. I just rewrote it differently, right, just to emphasize that you can write a vector like this, and whatever is multiplying doesn't necessarily have to be a constant. So you can be multiplying a vector by a function, and all that means is multiply everything in that vector by the function. So we want to compute the Wronskian of these things. So the Wronskian of x1 and x2. As we saw, all we have to do is put in the columns of the matrix as being the x1 and x2. Okay, so the first column is x1, that's e to the negative 2t, negative e to the negative 2t. Second column is x2, that's 3 e to the 60, 5 e to the 60. Okay. So as simple as that. x1 is column 1, x2 is column 2. This is a determinant, right? So we have the formula. So multiply the first diagonal. So it's going to be e to the negative 2t times 5 e to the 6t. And then subtract the product of the other diagonal. Right, so 3 e to the 60 times negative e to the negative 2t. Okay. Let's simplify this. So this is equal to, so we can add the exponents, right? So 5 e to the, just 4t minus, or plus, because we have minus, 3 e to the 4t, which is just equal to 8 e to the 4t. And again, this function, you can look at the graph, is never equal to 0. So since the Wronskian of x1, x2 is not equals 8 e to the 4t, which is not equal to 0 for all t, then x1 and x2 are linearly independent for all real numbers. So again, very easy to determine whether a set of vectors are linearly independent. I just have to calculate this once again. And if you have more than two vectors in with two rows, so let's say you had three vectors with 3 rows, you could just put this into Mathematica, as we learned how to do, to find what the Wronskian is. So very easy to determine whether vectors are linearly independent on an interval.